Ladies and gentlemen, welcome back to our postgraduate dynamics course, MSD 780. Today we are going to continue with the application examples. So in the previous lecture, we actually started off with these application examples and we considered the double A arm suspension system and the McPherson suspension as well. So these are two of the most common suspension systems in vehicles. We also looked at how we can actually go and apply the dynamics within Nikravesh's body coordinate simulation program. So today we're going to look at the card that is rolling on a flat surface. So we're going to look at some disc joints and how those are going to affect the overall dynamics of the system, and also delve into some of the Jacobian matrix, the details with regards to how we can actually set up our own Jacobian matrix. Now, before we do that, I'd like to quickly just give a brief review of something that we perhaps skimmed over in the previous application examples lecture, and this is with regards to how the DAP-BC system actually handles forces and moments that we specify on a specific body. Now, to illustrate this, I'm first going to open up the double A arm suspension, and what you'll notice from our exploded view over here is we actually assume that the center of mass of the wheel assembly 2 over here is in line with the spring stiffness, or the stiffness of the tire force that we're going to have over here. So in other words, whenever that force is going to act on the tire, it's also going to act through the center of mass, since its line of action is in line with the center of mass. However, this was not the case for the McPherson suspension system that we considered. So if I close this one and we go to the McPherson suspension, you will notice over here that we actually have the center of gravity situated a bit further from the actual center line of our tire. So our tire stiffness is instead going to have a force that's going to act over here at point C and no longer at the center of mass. And we need a way to actually go and redefine this force. So what the DAP-BC workbench states is that whenever we specify a user force and we supply the force over there, that force will be assumed to act at the center of mass. If the force is not acting at the center of mass, we're simply going to translate that force from whatever point it's working in to the center of mass, and then we also apply a moment. So if you remember from first year statics and perhaps second year dynamics as well, you'll remember that we can translate a force from one point to another. Then we simply have to also accommodate a couple moment that ensues from that. Okay, so if we go to Octave, I'm just going to open up the MP_A. So we did do 3 methods of the McPherson suspension system. For all 3 of them, the user force is going to look the same. So MP_A will be representative of the other 2 models that we also have. So if I open up user force over here and I zoom in a bit, you'll see that we still define the force using the deformation of the tire. And if the deformation of the tire is smaller than 0, we have some sort of a Y component for the force. And now we have our spring damper force as 0, so we assume there's no force in the X direction due to the tire, but there is indeed a negative Fy, or a reaction force, as a result of the tire stiffness. When we say bodies 1.f over here, and we say then bodies 1.f plus FSD, we basically take all the current external forces, or all the forces that are currently acting on body 1, and we add this additional external force over here. However, it is assumed that this force then acts at the center of mass. And we know from the McPherson schematic that we have that this is indeed not the case. So now we just have to go and accommodate a moment arm as well, or a moment couple, to ensure that when we translate this force to the center of mass, that the moment is also accommodated. So to do this, it's more or less the same as what we did for bodies 1.f. So it's still bodies 1.n equal to bodies 1.n. So all of the current moments acting on the body plus, and then what we have over here is then a shorthand notation for actually translating the moment as a result of the force to the center of mass. So what we do over here is we simply use points 3. If we go to in points, you'll see that point 3 is C1, and this is indeed what we also have in the mind map. Over here, C1 is located on body 1, so the wheel assembly, and this is where that force is acting. So we want to use its local coordinates, and we're going to rotate its vector and simply multiply that with our stiffness force that we have. So if I go back to user force over here, you'll see that we simply say plus S underscore ROT. So this is the S vector rotated. And we use point 3, which is then point C on body 1. Dot SP means we extract its local coordinates. And prime over here simply means that we use the transpose. Once we've stipulated where the point is and we have its local coordinates and its transformations over here, we simply multiply it with that spring damper force that we specified in the previous step over here. And in this case, the system has then sufficiently created an equivalent model of where the center of mass now has the force F, or this FSD force acting through it, and then also a moment to accommodate the translation of that force. Okay, so that more or less concludes the two suspension system examples that we wanted to look at. So today we're then going to move on to the cart rolling on a flat surface or a horizontal surface. Now this model, as shown in figure 8.9a, represents a cart containing a main body, so this would be body 1, and two wheels that are connected to the main body by revolute joints. The wheels are modeled as discs rolling on the flat ground without slipping, so we have a no slip condition that we need to accommodate for, and a driver motor rotates one of the wheels, causing the cart to move forward. And we'll see in a moment that it's on the rear wheel that we want to apply this driver motor. And we had some experience with these driver motors before. You'll remember from the pendulum rod that we considered, we had a relative rotation driver over there that we wanted to specify, and that enabled us to actually apply a torque or measure the torque for a given kinematic relation. Right, the individual bodies, the reference frames, and the defined points are then shown in figure 8.9b. So over here we still have our main body 1, and we have 2 points 1 and 2, and these are to accommodate the revolute joints between these two wheels or discs and then the main body. So we have in total 6 points over here. You'll notice that points 5 and 6 are on the circumference of this disc, and we're not actually going to use it to do any calculations, but we want to create this point so that we can visualize how these wheels are turning. So the main objective of this example is to show how to represent a motor either as a driver constraint or by a torque speed function. And firstly, we're going to have a look at cart A, and this is where we're going to simply apply a driver constraint, similar to what we did for the pendulum rod. So in this model, it is assumed that the rear wheel, body 2, rolls with a constant angular velocity of 2 pi radians per second in the clockwise direction. Since we are working with the clockwise direction, it's essentially an angular velocity of minus 2 pi radians per second. If I expand over here, we can see that to enforce this condition, we can employ a relative rotation constraint as a driver, which refers to function A for its analytical description and parameters. And function A we also used previously for the pendulum rod, but just to go through it again, we can have a look at section 7.2.8 in the PMD textbook, driver constraints. So a driver constraint can represent a rotary motor or a linear actuator, where instead of specifying its torque or its force, we specify its kinematics as a known time function. And then we know that if we specify its kinematics, then we can actually go and measure what the reaction force or torque is going to be as an output. So for a rotary motor acting about the axis of a pin joint between two bodies I and J, as shown in figure 7.9a, so this figure over here, a driver constraint can be defined as phi bold, and over here we say it's a driver function, a revolute driver, or a relative rotation driver rather, comma 1. So the 1 indicates that it applies one driver constraint to this system. And we can go and break this up into a difference in the angle, so that will simply be phi I, so the rotation angle of body I, minus phi j, which is the rotation of body j, minus f of t. And this is then an explicit function in terms of time that we want to specify for this relative rotation driver. And all of this should then be equal to 0 to ensure that the constraint is met successfully. So then we can also go and simply derive this twice. So if we derive it once, we end up with this angular velocity equation over here. And then if we derive it a second time, we have the angular acceleration equation over here. Now in our model, the body indices I and j can actually be represented by bodies 2 and 1 respectively. And if we go back over here, we can see that we have a relative rotation driver that we want to specify on the rear wheel. So it's going to work in between bodies 2 and 1. So in other words, the two bodies in question that we need to consider for our driver constraint would be bodies 2 and 1. So in our case, we simply then choose body indices I and j as 2 and 1 respectively, and then we can go and set up our DAP type A function. So to do that, we can first consider the general expression, and this should also look familiar. We have a function of time which is equal to c1 plus c2t plus c3t squared. So we need to go and calculate the three coefficients over here in order to perform the relative rotation driver calculation, or to at least define its driver constraint function. So to do this, we can first go and calculate C1, and we know at time t equal to 0, we've defined phi 2 at 0 seconds equal to 0. So we note that phi 1 of t is equal to 0 as well. The orientation of body 1 doesn't change. And we know this if we go back to our schematic over here. We actually chose the local coordinate system for body 2 so that the xi2 direction is in line with the horizontal x-axis over here. So that means that our starting angle for body 2 is 0. And we can also assume, it's a fair assumption to make that body 1 is not going to rotate. It's only going to be the wheels that will then rotate. So phi 1 will be equal to 0 for all times t. Okay, so if I go back to this one, then we can look at the driver constraint function f of t, which is equal to phi 2 minus phi 1. And this must then be equal to 0 minus 0 if we're looking at f at 0. So by substituting all the zeros into equation 8.1, it is then easy to see that c1 is equal to 0. So how do we get this? We simply say this is our function that we have over here. So if we say f of 0, then it's going to be c1 plus c2 times 0 plus c3 times 0 squared. So we're only going to end up with f of 0, which is equal to c1. And we now know from this function over here that f of 0 must be equal to 0. And that simply states that c1 must be equal to 0 as well. So next up, we can then calculate c3. And we know that phi double dot 2 at time t equal to 0 is also equal to 0. And the reason for this is simply the statement that we have over here, which says that this model assumes we're working with a constant angular velocity. So our angular acceleration needs to be 0. Now if I go back to this one, we know that phi 2 double dot is equal to 0 at time 0, and phi 1 double dot is in any case 0 because it's not going to have any angle changes. So the orientation of body 1 doesn't change. If we look at equation 744, then f double dot t is equal to phi 2 double dot minus phi 1 double dot. And we know this is once again going to be equal to 0, which we get from here, minus 0 for body 1 as well, and that is equal to 0. Now we simply have to go and substitute this into equation 8.1 again. So I'm just going to take equation 8.1, derive it twice, and what I should end up with is 2c3. and 2c3 is then going to be equal to 0, which means c3 is also equal to 0. Now finally, we can also calculate c2, and the time derivative of equation 8.1 is then f dot t, which is equal to the c2 plus 2c3t. We also know that c3 is then equal to 0, so f dot t has to be equal to c2. And if we now look back at equation 744, which is this equation over here, the first part or the first derivative, we can see that f dot t is still equal to phi I dot minus phi j dot. And if I substitute all of that in, I know that phi 2 dot is equal to minus 2 pi radians per second, and I know phi 1 dot is equal to 0, so I end up with minus 2 pi, which is f dot t. In other words, c2 has to be equal to minus 2 pi. Okay, so some fairly simple substitutions that we just have to do to find these coefficients. From the pendulum rod example that we previously had, they actually gave us the angular acceleration. And from there we were able to integrate it twice to end up with this function f of t over here. However, in our case, we're now working with a constant angular velocity for the cart. So in this case, we just have to basically extend or just basically change our approach to finding these coefficients c1, c2, and c3. Okay, so the only non-zero coefficient that we have over here is then c2, and that is simply equal to minus 2 pi. So now we sort of have all of the information that we need to set up our driver constraint function. And I'm just going to close over here, and then we can move over to exercise 8.6. So the exercise says that we need to review the input M files for this model and note that the initial velocities are all zeros. So if I go to Octave, just going to head to the command window, and we're going to start off with cart underscore A. And if I open up all of its input files, we can run through that. So the first thing that we want to look at is the inanimate input file. Now, with some of the previous examples that we did, we didn't actually define any points over here under inanimate because none of the points were really used for animation purposes only. However, in this case, we said that points 5 and 6 are the 2 points that we want to use for animation purposes. So if I go back to our schematic over here, you'll see that point 5 is located on the circumference of this wheel body 2, and point 6 is located on the circumference of body 3. And these points are not going to contribute to the actual dynamics, or we don't want to define a joint between any of these points, but we do want to use it to at least see how these wheels are rotating and whether they are indeed rotating clockwise as expected. Okay, so another important thing that we need to consider for any points that we specify on a body is that the DAP BC workbench, once it runs the animation, it will actually construct a line from the center of mass of the body to the point in question. So for example, if we consider point 5, we know it's a point structure, but then we say P5.body index or B index. So in this case, it's body 2, and then we give its local coordinates as well. So what the system will then do is create a line from body 2's center of mass to the local coordinate point that we specify over here. And we'll see how that's going to look in a moment when we run the animation as well. Once we've specified all of the animation points, we just have to group them together in this points underscore anim list. And this is simply P5, P6 that we're working with. In addition to this, we also want to perhaps have a better illustration of how the main body and the 2 wheels are going to look. So in that case, we have to go and change the shape properties of these bodies. So body 1 is going to be the main body, and its shape is a rectangle. In this case, it's denoted RECT. To just illustrate where we found this, if you go to Appendix B or the DAP BC user manual, you will see that if you want to specify a body as a rectangle, the properties that you have to give it in is the shape. So this is then RECT to denote it's a rectangle. Then you also have to specify the width and the height of that body's or of that rectangle that you're specifying. So the width will be taken equally from the center of mass. So if I specify the width as 0.4, then it will be 0.2 to the right and 0.2 to the left. And dot h will then be the height of this rectangle, so also from the midpoint or the center of mass, so it will be 0.1 up and then 0.1 down as well. For a circle, all that we need to specify over here is then the body dot shape, which is then circle, and then the body dot r, which is then going to be the radius of the circle as well. Okay, and that is essentially what we're doing over here for the three bodies that we're working with. So body 1 is a rectangle with a width of 0.9, a height of 0.2, and then we can also go and specify the color in terms of the MATLAB standard statements for the different colors. So in this case, we denote it as R. R is simply used to indicate it's a red color. And then for bodies 2 and 3, since they are disks, we are going to use circles for them. Both of them have equal radii of 0.1 meters over here. Okay, so if we don't specify the color of the body, then DAP-BC is going to assume the default color is black. So in this case, we expect the two disks or the two wheels to be black since we didn't specify colors for them. Lastly, we just have to remember to also specify the minimum and maximum bounds on our animation axes. So in this case, x is from 0 to 1.5 and y is from minus 0.5 up to 1. Okay, so perhaps just to illustrate where we get some of these properties from, I'm just going to go back to our schematic that we had over here. And in this case, you will see that we chose the global coordinate system to sit over here in the corner, in the left-hand corner. So it's on ground, and we now want to reference all of the body coordinates with respect to this global coordinate system that we have over here. So a few important things just to note is that the disk over here, or the wheel radius, is given as 0.1. And then we also know that the distance from the wheel's center to the center of mass of body 1 is 0.3. So the actual distance between these two wheels are expected to be 0.6. Okay, so in addition to that, the width of the body is also given as 0.9. So if we go back over here, what we essentially assume over here is, since this is 0.3, 0.3, we still have 0.15 meters up to here, and then another 0.15 meters up to here. So then it should be 0.9 in total. Okay, so that more or less concludes the inanimate input file. Next up, we also want to consider the in-bodies input file. So in this case, we once again want to specify the three bodies that we have. So body 1, which is our main body or our chassis of the cart, bodies 2 and 3, which are the two wheels. And in all of these cases, we specify the mass of the body. So in this case, it's given as 20 kilograms for body 1. Then body 1.j, so its mass moment of inertia is 5 kilogram meters squared. And then we also have b1.r over here, which is equal to 0.5, 0.2. And then its initial orientation is given as 0. So to understand how we get this, if we once again go back to our schematic over here, we now know that this is 0.3. So what we may assume is that we also have an additional 0.2 meters over here until we reach the global coordinate system. So in this case, if my global coordinate system is situated over here, I'm going to take 0.2 plus 0.3 to get the x coordinate of the center of mass of body 1. And then it's also going to be in the y coordinate system, it's going to be 0.1 plus 0.1, so that's 0.2 meters. So if I go back, I can see that that is indeed what I specified over here. Then for bodies 2 and 3, I just have to do some work back a bit from the previous coordinates that I had. So where we now know it's 0.5 to the center of mass, if we take that 0.5 minus 0.3, we get the distance to the first wheel's center. And we can assume also that the center of mass is in line with the geometric center of these wheels. So the first wheel, its x-coordinate is 0.2 at the start and 0.1 y-coordinate. And then for body 3, it will be 0.2 plus 0.3 plus 0.3. And what we're then going to end up with is 0.8 for the x-coordinate of body 3 and still 0.1 for the y-coordinate of the front wheel over here. Okay, and that is once again what we see over here. Right, and then we also just want to specify that the starting angle for both of these wheels are also 0. So we assume that the xi eta coordinate systems are in line or are situated horizontally with the global coordinate system. Okay, once that is done, we can then go over to in forces. So this is a fairly stock standard application of the forces. We only have weight acting on the system, so we just have a force structure, the type is weight, and we just include that in our master list for the forces as well. Then before we perhaps move on to in functs, I first want to have a look at in joints. So if we look back at our schematic again, you will remember that we had two revolute joints acting over here. So we have a revolute joint between points 1 and 3, then we have another revolute joint between points 2 and 4, and then we also want to specify that driver motor that rotates one of the wheels. In this case, it's the rear wheel, so body 2. So we expect to have 3 joints that we specify, 2 revolute joints and 1 relative rotation driver joint as well. If I go back over here, we can see that that is indeed what I have. So I have a revolute joint between points 1 and 3. So on the schematic, between points, it's between points 1 and point 3. So point 3 is just at the center of the wheel. And then the second one is between points 2 and 4. So if I check that, I can see the revolute joint is over there as well. Now another important thing that we need to consider is then this disc joint that I have over here, and this is commonly used whenever we have either gears that are engaging with one another. So whenever we have some sort of a non-slip condition, it might be for something like a gear rack and pinion system, or then in the case where we have wheels that are rolling on a surface without any slippage occurring. And this is a fair assumption that we can make for our current model as well. We assume no slip conditions. So for that, we then want to employ these 2 disc joints as well. So one for each wheel or each body that is rotating. So for that case, J3 is then still a joint structure. The type is now denoted as a disc. And for the disc, we need to give it a few different inputs over here. We first have to give it the body index, which is equal to 2. So that means that the first disk is body 2. J3.r, so that this will be the radius of the wheel that I'm considering. And then J3.x0 is where this wheel is starting. So in this case, it's 0.2 meters. And we know this as well from, if we go to in bodies, we specified B2.r, its x-coordinate as 0.2. Okay, so then for disk 2, which is then specified on body 3, we once again have the same radius. X0 is now 0.8. We once again get that from our in bodies file. And then over here we also specify P0. So in this case, we say it's 0 because it starts at a 0 orientation angle. If we don't specify P0, then 0 is in any case taken as the default. Once these 4 joints are now specified, then I can specify my relative rotation driver as well. And this is similar to what we did for the pendulum rod. In this case, we specify the type as this REL-ROT, so that's the relative rotation driver. Then we have a I body index and a J body index. And you'll remember from our calculations that we did, we said that body I is body 2 in our case, and body J is body 1. So I just denoted in this form. And then I just have to give the actual driver function as a final input. In this case, it's equal to 1. So if I go to my infuncts list, then you will see that I have only one function specified over here. In accordance with the calculations that we did previously, we said we're working with a type A function, and if we now specify its coefficients, we have C1, C2, C3. So it's going to be 0 minus 2 times pi 0. And this we got from the calculations as well. Okay, so that is then in joints. In points is then simply the actual points that I specify, which I'm going to use in the dynamic analysis. So I have 4 points over here, point P1 to P4. And if we go back to the schematic, you'll see point 1 is specified on body 1. Point 2 is specified still on body 1. So what I expect is the DAP BC to actually construct a line from the center of mass to point 1, and then also from the center of mass to point 2. And then I also have points 3 and 4, so these are located at the center of mass of each of these wheels. So instead of having a line to the point, it's simply going to denote a point at the center of mass. Okay, so these are then just grouped together once again in a final list. And lastly, I then have the in-U vectors input file, and over here it's simply an empty list because we don't have any translational joints that we want to specify, so it's not necessary for us to specify any U vectors either. Right, so now that that is done, we can then execute DAP and ask the program to correct the initial conditions. Then we can execute anim and observe the animation of the response. So if I do that, I can go over here, and I'm first going to clear all, close all, just to make sure that I'm working with a clean workspace. Then I'm going to type in DAP. It asks which folder contains the model. So we're first considering cart_A. So I'm just going to type in cart A over here. And then it asks whether I want to correct the initial conditions. In this case, yes, I do want to. And what you'll notice is that the X, Y, and Phi coordinates that I specified for the 3 bodies are still correct as I specified them in the in-bodies file. However, X dot, Y dot, and Phi dot changed for the bodies. The reason for this is I actually didn't give it any input, so if I didn't do any initial condition correction, the DAP BC workbench would assume that these values are all 0 based on the default. However, in this case, I now did initial condition correction. So it says, since I'm working with a constant angular velocity, I now need to correct the X dot, Y dot, and Phi dot values over here. Okay, if you also want to go and check the values over here, we know that Phi dot should be minus 2 pi radians per second. So in this case, we can sort of qualitatively validate that that is what we get. Minus 6.2832 is indeed minus 2 pi radians per second for the 2 wheels that we have over here. Okay, so then it asks for the final time, and I'm perhaps just going to say 3 seconds, and I'm going to use a reporting time step of 0.1 seconds. And now we can see it performed 81 function evaluations. So now I can just go and type in anim. And an important error that it gives over here, and if you're working in Octave, then it's probably going to say cylinder length R must be larger than 2. And this is where a distinction comes in between the MATLAB and the Octave specifications in the inanimate file. So if we go to inanimate, whenever we specify a circle, we need to make sure to specify bodies2.r as an actual list. So we're simply going to say over here 0.1, 0.1, and then over here we can also say 0.1, 0.1. And if I perhaps just run this again, so I'm going to say dap card underscore a. Yes, I correct the initial conditions for a final time of 3 seconds, a reporting time step of 0.1, and if I animate it, then we can see that this is indeed what I now get. So at least now I get some sort of an output. So if you were working with MATLAB, you would have just said .r equal to 0.1. In the case of working with Octave, you're going to have to give it as a list containing 2 equal values. So 0.1, 0.1. Okay, so if I now, let me perhaps just do close all, and then I'm going to say anim again. Okay, and then I can press a key and see what happens to this system over here. Okay, so what I can see in this case is that the card is now moving out of the actual limits that I specified. So I can do one of two things. I can either make the time step or the final time a bit shorter, and to do this I'm just going to minimize this. So I can either use a 1 second time step, and this will actually allow me to also check whether I do indeed see the minus 2 pi radians per second velocity. My expectation is that if I start with that horizontal line from the center of the wheel to the circumference, and that line is horizontal, then after 1 second it should also be horizontal again. And the reason for that is it then made a minus 2 pi radians rotation, so a single rotation of the wheels. Otherwise, I can also go and change the inanimate file, and I can use different axis limits. Unfortunately, if I'm not interested in perhaps 3 seconds, but I'm interested in a shorter time, then it's still going to take quite a while for this thing to animate. So in my case, instead what I want to do is perhaps just rather animate it over 1 second. So I'm just going to say clear all, close all again. I'm going to type in DAP. Once again, it's card A that I'm going to consider. I want to correct the initial conditions. I'm going to use a final time of 1 second, and let's perhaps still use a reporting time step of 0.1 seconds. Okay, and now we can see the number of function evaluations are also slightly lower at 69. So then I'm just going to run anim, and if I press a key, then I can just go and check. So I now know that this line from the center to the circumference started horizontal, so I expect after 1 second that this point is then going to be horizontal again, or this line is going to be horizontal again. Okay, so if I now go and check, I can see that it now terminated, so that is indeed correct. So this line started horizontal and it made a single clockwise revolution until this line was horizontal again. So that's then fine. Okay, so in the animation, and I perhaps just want to show a single animation schematic over here, we can now also see that point 1 or this center of mass is indicated over here in the same color that we indicate the rectangle in. And then any points that are situated on this body are connected to the center of mass via these lines. So this is indeed what we expect for the DAP-BC workbench, and we can also now go and validate that there is a connection between the points, so that is fine. Right, so that then concludes that step that we wanted to do. So we now observe the animation of the response with the corrected initial conditions. If I just expand over here, this is basically just a discussion of the inanimate that we went through, so you're more than welcome to read through that. Then we can also go and consider the program anim. So the program anim displays the body mass centers and all the defined points as small circles. And like we said, the program then draws lines between a mass center and every point that is defined on that body. The assigned color to a body will be used for the lines as well. If we don't specify a color, then the default of black is taken. We can specify a different color based on the MATLAB's color abbreviations. So if you're familiar with the color coding that you use for the plots that you generate in MATLAB or Octave, then those same color codings you can use for changing the color of the actual bodies. Right, so then a bit more information regarding the circular disc, and you can also refer to the PMD textbook section 727. A rigid circular disc rolling on a flat surface, as shown in figure 7.8a, could represent a wheel rolling on the ground. So figure 7.8a is this one over here. So we have some sort of a disc rolling on ground, and it has its own xi, eta local coordinate system as well. To ensure that the disc remains in contact with the ground, a constant or a constraint such as yi minus ri equal to 0, where ri is the radius of the disc, can be defined. And for this, we can consider section 7.2.6, which deals with simple constraints. So a simple constraint is a condition imposed on one or more coordinates of a body. For example, if the y coordinate of a typical body I must remain equal to 0.25 meters, we write a simple constraint as yi minus 0.25 equal to 0. So it's significantly more simplified than the constraints that we've considered up to now, especially for the kinematic joints and the more complex driver constraints that we're going to look at later on as well. Since a body has 3 coordinates, any of the following simple constraints can be imposed on a body. So we can either have it in the x direction, in the y direction, or in the phi I direction, or rather just in rotation around the z-axis. And we can also have a combination of any of these equations for 738. So C1, C2, and C3 are constants. The velocity and acceleration constraints for these simple constraints have trivial forms, which yield in the x direction we have this Jacobian over here, in the y direction we have this Jacobian, and in the phi direction, so rotation about the z-axis, we have this Jacobian over here. Okay, so to ensure that the disc rolls without slipping, a constraint for no slip must be enforced. The no slip condition can be viewed as the relationship between the rotational and translational velocities of the disc. So what I can say over there is Ri phi dot I is equal to minus x dot I. So this is simply an extended version of the V equal to R times omega equation that you are perhaps more familiar with. In this case, we just need to note that when the disc rolls counterclockwise, so in other words, we have a positive phi dot I, it translates to the left. So in other words, we have a negative x dot I, and that's the reason why we have this negative sign in front of x dot I. The integral of this relationship provides the position constraint for the no-slip condition in this form over here. So once again, we have phi, it's a no-slip condition, and it imposes one constraint over here. And we can write it in this form 740. And for this equation, subscript 0 xi and subscript 0 phi I are the initial x and phi coordinates of the disk. Okay, and you'll remember if we go back to our in joints file that we had over here, for a disk, two of the things that we need to specify is x naught and then also p naught. So these are the two inputs relating to that equation over here. The r that we specify is from this previous step that we have over here, where we enforce this simple constraint yi minus ri equal to 0. So we simply also have to give it this dot r argument in as well. Okay, so the corresponding Jacobian matrix and the right-hand side of the acceleration constraint are then given in this form over here. So this is equation 741 that then provides for the no-slip constraint. Okay, so we expect a disk to actually enforce two different constraints. If we consider, I think if we go back to this one, we actually consider that there's a no-slip condition. So in other words, we expect some force over here between ground and the actual disk. And then we also expect some reaction force over here due to the wheel being in contact with the ground. So it's a sort of a normal force that we consider as well. Okay, so if we now look at the solution, this is just an iteration of what we went through as well. And we can note that since the angular velocity of the wheel is minus 2 pi radians per second at t equal to 0, we need to provide correct initial velocities for all the three bodies, or ask the program to correct them for us. In our case, it's a bit easier to request the DAP-BC workbench to correct it for us. Otherwise, we would have to go and manually work out these values, x dot and the phi dot values as well. So when you ask the program to correct the initial conditions, you receive the following corrected values. We can see that x, y, and phi remains as we put it in, but the corrected velocities, however, now changed. It is no longer the default value of 0. It updated so that it attains a constant angular velocity of minus 2 pi radians per second, and this is validated from this phi dot value for both bodies 2 and 3. We note that the coordinate values have not been changed, but the velocities have in any case, or have thus been changed. Okay, so that is in line with what we expect. Okay, so then we just performed the animation and we saw what basically happens with the with this exercise 8.6. So since we corrected the initial conditions, we did indeed get the proposed motion. So exercise 8.7 now says that we want to execute DAP, but we do not ask the program to correct the initial conditions. In other words, we keep all the initial velocities at 0. And we want to perform an animation of the response, and we want to see what we observe for the motion of the system. So to do that, I'm just going to say clear all, close all again. Then I'm going to type in DAP. I'm still going to model card A, and now I don't want to correct the initial conditions. So I'm just going to type in N, and we can see it now says redundancy in the constraints. So something tells me that there's going to be an issue. Either some of the constraints are going to break, or the system is simply going to seize up and I'm not going to have any motion at all. So if I still use a final time of 1 second and a reporting time step of 0.1, then it runs for 63 function evaluations, and now I just want to go and run anim again. Okay, so if I press a key over here, then we can see in this case it seems to remain stationary. We don't actually have any motion of this system. And we're going to look at why this is the case in a moment. Okay, so they're now completed, so we can just close all over here. So we see that if the angular velocity is not corrected, then the system is simply going to remain at rest. And now the question is, why is this the case? And for that, we can actually go and have a look at the solution. So we observe that nothing moves, even though we have a driver stating that the angular velocity of body 2 is minus 2 pi radians per second. The reason for this is that when we solve the equations of motion, we only enforce the second time derivative of the constraints, including the driver constraint. So if we refer back to lecture 4, where we listed the position constraints in equation 1319, the velocity constraints in 1320, and the acceleration constraints in 1321, we also had the addition of the equations of motion in 1322. So these are the list of equations that we're working with. Now what this basically tells us is that we are only enforcing the acceleration constraints in this case, or the acceleration of the system. Hence, even though we specify a constant angular velocity of minus 2 pi radians per second, it's going to be a constant or a zero angular acceleration. But even if it starts at 0, it's still going to be a 0 acceleration as well. So it says, why do I need to correct it if I in any case get a 0 angular acceleration? So the second derivative of our driver constraint enforces phi 2 double dot equal to 0. So if we start the simulation with a 0 angular velocity, the driver acceleration phi 2 double dot equal to 0 will keep the velocities unchanged at zeros, since it technically already satisfies this constraint that we enforce on the acceleration. Okay, so to make sure that we have continuity across our kinematics, we also need to perform this initial condition correction, and that is once again why it's more practical or better practice to make sure that you always do some sort of an initial condition correction, even if you know that your values are correct. Alright, so this more or less wraps up everything that we wanted to look at for card A. So in this case, it was a straightforward driver constraint or driver function that we specified on the system. The next card that we're going to look at, card B, will then deal with the torque speed function that we want to consider, and also have a bit more in-depth look at the Jacobian matrix. So that will be presented in part 2 of this lecture.